Good afternoon. My name is Young-Sik from KAIST in South Korea. Today, I will introduce active SSDs architecture which improve the performance of active sorting using on-the-fly data merging. My environment data-intensive computing. Data-intensive computing is a class of applications which use a data parallel approach to process large volumes of data. The demand to process large volumes of data is increasing in various areas such as web search, social network service, e-commerce, scientific analysis, and so on. Because of this, researchers and companies have proposed and optimized the data-intensive computing architecture. Google's MapReduce and Apache Hadoop are two famous data-intensive computing architecture. Note that because data-intensive computing handles large volumes of data, it generates best amount of I/O. So improving the I/O performance becomes important. One way to improve I/O performance is using fast storage device, that is solid-state drives. Compared to the traditional hard disk drive, SSD have many advantages, among them fast I/O performance and low power consumption. So SSD are used for improving the performance and save energy in data-intensive computing environments. To further improvements in data-intensive computing, people have applied InStorage processing into SSD. In the traditional approach, the host processes all the data and regards the SSD just as a storage. So the host reads all data from the SSD and processes the data and writes the result to the SSD. After that, when the request from the next processing arrives, the SS sends the result to the next processing. So there are high amount of data transfer between the host and the SSD. On the other hand, if the SSD can process the data by itself, the result can be computed by InStorage processing without any data transfer between the host and the SSD. The only data transfer to the host is sending the result to the next processing. So by uploading the data processing function, SS can reduce the data transfer between the host and the SSD. As a result, InStorage processing improves the performance and save energy. There are many works which propose InStorage processing architecture schemes. A few examples are fast scan, intelligent SSD, active flash, and smart SSD. But these work only consider the case of using aggregate function as offloading function in SSD, such as scan, sum, min, max, count. In this case, the size of the result is very small. So very small amount of traffic is required to deliver the result to the host. They exploit this point to improve the performance of data-intensive computing. However, in our approach, we propose a method to reduce the amount of I/O with general data processing, including non-aggregated function. Our approach is that our approach is called active SSD. Using InStorage processing, we process the result on the fly when the request from the next processing arrives. In this figure, active SSD gives the illusion of having the result, but actually it does not exist. When the request from the result arrives, active SSD processes the result on the fly and passes the result into the next processing directly. So active SSD can eliminate extra data transfer required to write result, reducing the amount of write, also increase the lifetime of SSDs. To verify our approach, we study external sorting as an offloading function. Resource sorting is a widely used sorting algorithm for large amounts of data with limited memory size. For example, the Hadoop framework uses external sorting as the core function. This figure shows the general process of map and reduce space in Hadoop. When the map function outputs the intermediate data, Hadoop uses external sorting to sort this data. To prepare the input for the reduce function, Hadoop also uses external sorting by merging several map functions output. I explained the details of data transfer in external sorting. To sort data, the input data is divided into several chunks using the available memory size. Then each chunk is sorted using an in-memory sorting algorithm, and then each sorted chunk is written into the disk. Next, the sorted chunks are read and merged to generate the complete sorted data in the host. The final sorted data is written back and then is written into the disk. Finally, the source data is read again to use in the next processing. As you can see, there are many data transfer since external sorting lies intermediate data and the result to the disk. Even if the page cache is used, there are double amount of write. To reduce the amount of I/O, we modified the process of external sorting using on-the-fly data merging. We call this process active sort. The first page to generate partially sorted chunk of data is the same as traditional external sorting. However, in active sort, the merge function is executed inside of the SSD as an offloading function and generates the result on the fly when the request from the next processing arrives. By doing this, we can remove the extra data transfer to write result compared to the traditional external sorting. Even if the page cache is used, active sort can replace the amount of write with read. For the experiment, we used a host machine equipped with an Intel CPU and 16 GB RAM. The actual user memory was restricted from 1 GB to 3 GB by booting option. For the implementation of active sort, we used the OpenSSD platform, which provides an open source environment for SSD firmware development. It consists of an ARM CPU, 64 MB RAM, and 4 flash memory modules. This platform supports SATA to connectivity, and we modified the simple page mapping FTL to support active sort. To use active sort, many parameters from the file level are required inside of the SSD, such as the location of file and the size of key and records. To get this parameter, we simply fix the location of partially sorted chunk files and file up, and key and record configuration files in SSD. I show the detailed implementation of active sort inside of active SSD. The flash memory controller reads the partially sorted chunk, which is always stored in the flash media. Then fills the contents into a temporary buffer in DRAM inside of the SSD. We use multiple depths of temporary buffer to maximize interleaving efficiency. The embedded CPU compares the key and copies the write record into the output buffer to transfer to the host. This cycle is executed until all of the partially sorted chunk is processed. Because the flash memory controller and the embedded CPU can execute concurrently, we can reduce the avoid of merge function. This graph shows the bandwidth of sequential read and write using the OpenSSD platform. We also measure the bandwidth of on-the-fly merge function with sorted data and random data. For the case of handling sorted data, on-the-fly merge can use full bandwidth of NAND flash. So the result shows the overhead of compare and copy. In case of random data, the result shows the efficiency of interleaving, because sometimes it must read 2 or more records from the same chunk due to the random distribution. In the current implementation, our active sort has an overhead compared to normal read. But we can show the benefit of active sort because the bandwidth of the on-the-fly merge is still higher than write bandwidth. For the sort benchmark, we measure the performance of active sort, and quick sort. Nsort is a famous sorting library using external sorting, and quick sort is in-memory sorting function or the standard library in the Linux. This graph shows the elapsed time to sort and read for 2 GB set with memory size from 1 GB to 3 GB. You can see that the result of quick sort is very slow because there is high subtract. For the active sort shows stable result over the range of memory size. And active sort performs better than nsort because of reducing amount of I/O. It is interesting that the result of active sort is similar to the result of quick sort when memory is sufficient. That means by using active sort, we can get good performance with low-end CPU and small memory size. In the 3 GB case, you can see that the result of nsort is similar to the result of quick sort. This is because nsort performs in-memory sorting when the memory size is sufficient to handle entire of data set. This graph shows the amount of I/O when the memory size is 1 GB. You can see that because active sort can reduce the amount of I/O by on-the-fly data merge, active sort requires a smaller amount of I/O than nsort. There are many things to improve our active SSDs. First, optimization of on-the-fly data merge. The OpenSS platform that we currently use has very low computing power. So by using more cores or memory and high internal bandwidth as with the modern SSD, it is possible to reduce the overhead of on-the-fly merge. We also consider the support of specialized hardware to compare and copy. Next, offloading the entire sorting process. That is ultimate approach to generate the result on the fly. Third, considering the case of using multiple active SSDs. The scalability issue is important in data-intensive computing. Finally, developing a general API to pass parameter for active SSD is required. The object-based interface is one solution to get the file-level information inside of the SSD. In conclusion, we propose active SSD architecture which use InStorage and on-the-fly data processing. By studying the external sorting case, we showed that active sort can eliminate extra data transfer. As a result, active SSDs can improve the performance and increase the lifetime of SSD by reducing the amount of write. In the near future, we'll integrate active sort into the Hadoop framework because Hadoop uses external sorting as the core function. So we can increase the performance of Hadoop by active sort. Finding more uses of active SSDs with on-the-fly processing is also important to make a complete work of our approach. Thank you for attention, and this is my email.
Hi, this is Pradeep Kumar from George Washington University. So I have a question regarding the lifetime that you discussed, that it can improve. The lifetime of the SSDs can be improved. So do you have any quantification, like how much it can improve, and what is the theoretical logic behind that, that SSD's lifetime could be improved utilizing this technique?
Sorry, my improvements just focus on reducing the amount of I/O.
So I/O is reduced between the host and SSD, but still the controller will read the data from SSD to controller DRAM.
Yeah,
and when you sort it, you again will write back it to SSD.
Yeah.
So my belief is that the SSD lifetime may not improve, or if it will improve because of the additional DRAM that you are proposing to increase the DRAM in the memory controller.
Yeah. In the case, we expect we can utilize the internal bandwidth of inside of the SSD.
Right.
So you can, in the case, we can improve the performance.
Yeah, performance I agree. Yeah.
Okay.
So I was wondering, you mentioned trying to find other applications.
Yeah.
Do you have any thoughts about what applications there might be for this technique, or what characteristics those applications would have?
Yeah, that is a good question. So after I submit the paper, I try to find that, but so far I can. For example, the keyboard store, compaction of keyboard store is, I think, the one example to this model. But that is not just on the fly data, not suitable for on the fly approach. That is just in-storage processing.
And did you measure the bandwidth? You have performance numbers on on how much faster you made sorting, but just for the bandwidth of reading the data out and merging it, how does that compare with reading out the data if it's already sorted? I'm thinking about situations where you might want to read the data several times, and so where is the trade-off there?
So the second is just normally.
Okay.
Yeah, and the last is the read with margin.
Okay.
So there is some overhead to get the sorted output, but we can reduce the overhead. And if you use the multiple reads for sorted output, you can generate the result and save to the disk for multiple reads.
Okay.
Yeah. So, yeah.
All right. Do you have other questions? Okay, thank you.
Thank you.